Hello there, this is Truth Socrates. Welcome to video number 37 for my series on multivariable calculus, which is known as Math 5C at Pasadena City College. So in our last video, we talked about the divergence and the curl of a vector field. And we used it in order to find two equations which were equivalent to Green's theorem, the conclusion of Green's theorem. So in one of those equations, we see the divergence, and in the other one, we see the curl. So today, we're going to see why these two equations are relevant, starting with the equation involving the divergence. So I will see you on page 328, where we talk about the divergence theorem. All right, so this is the form of Green's theorem that I was telling you about. Let's read it from the beginning. From the very top. Suppose that a domain D is a closed and bounded region on the xy plane, which is either a type 1 or a type 2 domain, or a finite union of these domains without holes. Okay, holes are a problem. Let C be the boundary curve of the domain D, and we give it the positive orientation. Okay, so remember that means that as you walk around the curve, the domain, which is like a swimming pool, should be towards your left hand. Okay, so we write this as C is the boundary of D. Okay, suppose that F is a field in two variables with components P and Q, and they are continuous, and they have continuous partial derivatives as well on an open region which contains the curve and the interior D. Then the contour integral around C in the positive direction of the field dotted with the outward normal vector of the domain ds is equal to the double integral over the domain of the divergence of f. So this is the conclusion of Green's theorem written using the divergence of the vector field. Okay? Here is now Gauss's theorem, the divergence theorem, and of course, Carl Friedrich Gauss is one of the greatest mathematicians and physicists who has ever lived. Okay, and there you go. I want to show you how similar these three parts of that equation are to this conclusion for Gauss's theorem. Okay. So instead of a contour integral, we have a flux integral. And instead of a double integral here, dA, we have a triple integral, dV. Okay? So, in full, here it is. Suppose that E is a closed and bounded solid in space, which is either type XY, type XZ, or type YZ, or is a finite union of these solids, again without holes. Okay, so we write S is the boundary of E, and we give it the outward normal orientation. Okay, so when we did flux integrals, we said you have to specify the orientation of the surface. Okay, do you want the normal vectors to be pointing up or pointing down, pointing in or pointing out? Okay, so in this case, we want the boundary of the solid to be pointing outwards. The unit normal vectors will be pointing outwards, away from the solid. Okay? So again, F is a vector field, this time with three components in X, Y, and Z. And again, you want the components to have continuous partial derivatives on an open region that contains the solid. Okay. Then, the flux integral of F over the surface, again given the outward normal orientation, must be the same as the triple integral over the solid of the divergence of our vector field. Okay, so this is a great theorem for many reasons, and let me be honest, this appears in Maxwell's equations in physics. Okay, so what we're going to do today, it's not really what this theorem is used for. It's really useful in physics. Okay, so For us, though, it's going to be useful because, as you just experienced a few days ago, the flux integral can be kind of, complicated to set up. Okay, it could be challenging. Okay, you have to parameterize your surface. You have to take the partial derivatives. You take the cross product, plug in the components into your function, and then that's the time when you can integrate. Okay, triple integral it's not so bad. Okay, we know more or less how to set up a triple integral, but of course today we're going to review how to do it. Okay, hopefully you can follow along, but if you need more details, we have a video for that. Okay. Also, the divergence of a vector field is no longer a vector field, but rather it's just a scalar function. Okay, and because we're taking partial derivatives, some terms might completely disappear, and some powers could go down. Okay, so if our vector field were only contain polynomials in its components, then the partials will be simpler. Okay. So let's go to our workroom and let us go over an example, and maybe you'll recognize the solid that we encounter and how to integrate it. Okay, so here is our problem. We will use the divergence theorem to find the flux of this ugly looking vector field through the four sides of the tetrahedron. Remember those? With vertices the origin, 2, 0, 0, 0, 5, 0, and 0, 0, 4, we give this the surfaces of the tetrahedron the outward orientation. Okay, so the divergence theorem requires that the normals are pointing outwards. But what if they were pointing inwards? Is that so bad? No. Just reverse the problem, and at the end, after you compute the triple integral involving the divergence, just take the opposite side. Okay, take the negative. We saw this in Green's theorem, where we said, well, Green's theorem says you have to be positively oriented, counterclockwise, more or less. Okay, if you're going clockwise, big deal. Just take the negative at the end of the integration. Okay, so we're going to go to GeoGebra in a minute. We're going to see how this tetrahedron looks like and how we can integrate over it. You might remember it's a simple solid. It can be expressed in all 6 orders of integration. So the order that we choose will depend on what we are integrating. Okay, so the divergence theorem says compute div f, that's why it's called the divergence theorem. And remember, you take the partial derivatives of each component with respect to the variable referred to by that component. Okay, so this is the x component, y component, z component. Take the partial of this with respect to x. Okay, so yeah, let's start. What is div of this f? Okay, partial with respect to x. So I see 7y. That disappears. 2x becomes plus 2. Okay, so see what an improvement that is. Okay, this ugly term is gone. Next, partial of the second component with respect to y. So that disappears. This one becomes minus 6y. Z squared disappears. Excellent. Last term, partial of the third component with respect to z. So there's a plus 5. 2yz becomes plus 2y. And 6x to the 5th y. Oh, thank goodness. We're taking partial with respect to z. So that goes away completely. So what have we got here? 9 minus 6 is 3y. And 2 plus 5 is 7. Okay, so the divergence of f is very simple. And it contains only one variable, y. No x, no z. Okay, did we do this correctly? You know how I make mistakes. So, it was being temperamental. Screencast-O-Matic must be interfering with the operations here, but I clicked it for us. So the divergence is correct. It is 3y plus 7. Okay, so now let's move on to GeoGebra, and let's see what would be a good order with which we integrate the solid. How will we set up that triple integral? Okay, so well, thinking about the divergence, it only contains y. So therefore, remember what we did when we did triple integrals. If you put y in the inner, then you're going to integrate y right away. And then 3y will become 3y squared over 2. You complicate the problem right away. So we postpone it until the very end, the outer integral, so that when we integrate with respect to z or with respect to x in the inner or middle integral, then this is just constant. Okay, so we will definitely integrate y on the outside, and let's see if we want to integrate with respect to x inside or z inside. All right, so I already entered the vertices and created polygons that make up the sides of our solid. Of course, they're just triangles. Okay, so we said we will save y for last, so we will need a type xz double integral on the outside. Okay, so there is our x versus z. Yeah, it's not very difficult setting up that domain. And then we need to do y. Okay, so remember how to do this. We shoot arrows through the solid parallel to j, positive y direction. They all enter on the the xz plane where y is 0, okay? And they all exit on the inclined plane over here. So we will find the equation of that plane and we will solve for y, okay? And that will be, I'm sorry, back up. So our y will go from 0 to 5 on the outside, okay? And then we'll have to decide whether we take x or z in the middle, okay? So how about we take x, okay? So y on the outside, x in the middle. So we will solve for x in terms of y. Yeah, and no, it's not a type xz solid that we want. It's a type xy solid, okay? And then we solve for z, again, on the inclined face of our tetrahedron. Woo! Okay, that is a good catch. So y on the outside, x in the middle, and then z on the inside. All right, so let's continue. Let's start with our y. So y will go from 0 to 5, and we have dy on the outside. Okay, and then we will have x in the middle. Okay, so we have dx in there, and then we will have z inside. So integral dz on the inside. Okay, right there. Okay, so let's complete our outer double integral. We have x versus y. So we'll need the triangle formed on the xy plane by these 3 points. Okay, so of course those are the intercepts 2 and 5. So we have x over 2 plus y over 5 must be equal to 1. So solving for x must be 2 times 1 minus y over 5. So let's write it like that. Okay, so x versus y, we have that triangle. So y goes from 0 to 5, and then we put horizontal arrows pointing towards the positive x-axis. So intercept x equals 0, and exit at this line. So we put that limit over there. Shall we blow this up a little bit? Okay, there you go. Oh, no complaints from scientific notebook there. Okay, so similarly, we want to solve for z, okay, from the plane. So the plane is almost complete. We are missing z over 4. Okay, so now solving for z, we have 4 times 1 minus x over 2 minus y over 5. So that can go right over there. Okay, so that will be our upper limit. So below you have 0, okay, entering on the xy plane. So we enter at z equals 0, and we exit at this triangle, okay, the equation of the plane containing that triangle. Okay, so our div f is over here. So that is our triple integral. Okay, so the rest, of course, is what? Is that chapter 3? Yes. Chapter 2 was double integrals. Chapter 3 was triple integrals. There are no quadruple integrals. Okay, so more or less you know what to do. What's the final answer? Let's just click on it. Ooh, 215 over 3. What an interesting number. Okay, so yeah, of course the inner integral. Okay, let's start out the process. Integral with respect to z, so it's just z, and then we integrate from 0 to up here, but there's nothing down there, so when we plug in z, this is the only one that matters. Okay, there you go. So that is our inner integral, and we are done with that step. Okay, so of course we can factor out the 4 if you like, or you can distribute it in. It'll at least get rid of the 2 over there. But yeah, if you don't mind fractions, then you can just keep that. So keep that factor out. So there we go. And of course now we will have to expand this thing. Okay, so we are now in chapter 2, double integrals. Okay, so who are we? So let's see if it doesn't act up this time. So let's expand. Could be because my my border is so close to the control. So that is the double integral that we're gonna have to, that you are going to have to compute. Okay, so integrate with respect to x, that becomes xy, x squared over 4, 7, another x squared over 4, 3 is xy squared plus 7x, and so on. Okay, so you remember what a mess it could be, okay, but at least we know the final answer. All right, so I wanted to walk you through, it's not quite a proof of the divergence theorem, but basically what is the intuition behind why the divergence theorem is true, okay? So let's take a look at the simplest kind of solid, okay? So back in chapter 3, these are probably the same diagrams, and we have a brick, a solid brick, from 1 to 3 along the x, minus 2 to 2 along the y, 1 to 3 along the z, okay? So the boundary of this brick is made up of 6 rectangles, okay? Top, bottom, left, right, front, and back, okay? So we would have to parameterize 6 surfaces if we wanted to find the flux of a vector field through the 6 sides of this brick, okay? How would we parameterize the top and the bottom, okay? So z is from 1 to 3, so we'll need a rectangle at z equals 1 and another rectangle at z equals 3, okay? So of course, rectangle in this case along the x and y, so here are your domains for u and v, okay? So we know how to parameterize rectangles, okay? So similarly for left and right, front and back, okay? What are the partial derivatives for these surfaces? Okay, so partial with respect to u, we'll get 1, 0, 0, which is I. Partial with respect to V, same one, is 0, 1, 0, which is J. Okay? So of course, when we take the cross product, we get K. All right? So the normal vector from this parametrization for the top surface would be positive K. All right? However, wait a minute, we have exactly the same parametrization down here for the bottom. Okay? So we will also get K as the cross product of the two partials. Okay? It doesn't matter what the z coordinate is. Okay? But Gauss's theorem says that we need to be pointing outwards. Okay? So instead of positive K, we have to choose negative K for the bottom. Okay? So I have some visual aids over here. This is the best I could do for a brick. Okay? TCU. Anyone? So, for a brick, okay, we're going to do outward normal vectors. Okay? So on the right side, we're going to point to the right. Well, I guess to you, that's your left. Okay? And same on the other side, it has to be pointing outwards. At the top, you have to be pointing upwards. At the bottom, pointing downwards. If this is your front, then you want to be pointing outwards. And at the back, pointing towards the back as well. All right, so this is the same brick, and now we see the correct outward normal vectors. Okay? Point away from the solid, and you want to be perpendicular to the respective side of that solid. Okay? So what are we going to do? We are going to use the description of the divergence in the previous section, and we're going to imagine subdividing our solid brick once again into partitions. Okay? So divide AB into L subintervals of equal width delta x. Same for Y. Subdivide CD into M, I believe, subintervals of width delta Y. And similarly for RS, subintervals of width delta Z. Okay? So in chapter 3, we use the concept of a triple integral to find the mass of a solid given its density. Okay? However, we said that in the previous section that the divergence of F has this interpretation. Okay? The flux of your field through the 6 sides of this really, really small subbrick divided by the volume of that brick, and you let that volume go to 0. Okay? That flux is the divergence of your vector field through at that point. Okay, at the point in one of the corners. Okay, I believe the lower back left corner of that brick. Okay, although of course because the size is getting smaller and smaller, it doesn't really matter which corner you pick. Okay, so yeah, this this formula, okay, should remind you a little bit of our interpretation of density, okay? Because if you now solve for the flux, okay, the flux here is approximately the divergence times the volume of that itty-bitty little brick, okay? So, yeah, look at that. There's delta V here, there's a delta V over here, okay? So, yeah, that's not a mass though, okay? But, yeah, the idea is it's just about the same, very similar. Okay, so what we're going to do is we are going to build this enormous brick together, assemble it together, like Legos, actually. I was thinking about Legos when I was making these diagrams. Don't they look like Lego bricks? We're going to build them slowly, literally, one brick at a time. Okay, so let's start at the back left lower corner brick. Okay, It's literally like making a brick wall, except a brick wall usually is just one layer, okay? One thickness rather, okay? So you do build up bricks, okay? This is ridiculous, right? But we will also build them side by side, okay? So that you can have several bricks going left to right, okay? All right, so how would we put these first two bricks together, okay? So we have this brick and then this brick. Okay, we're going to stick them together like that, okay? One small thing though, okay? What we're interested in is the flux of our vector field through the 6 sides of these 2 bricks, okay? So there are 6 sides here. There are 6 sides over here. You have the flux of your field through the 6 sides each, okay? But what did we say? On this side, you have to be pointing outwards, okay? On this other brick, we're going to stick it to this side. You also have to be pointing outwards. Okay, so guess what? The normal vectors of those 2 sides will be pointing away from each other in opposite directions, okay? So therefore, what's going to happen to the flux, okay? The flux over here will have a normal vector in this direction. The flux over here, we have exactly the same field, okay, because these 2 sides are really the same point in space, okay? So over here, the flux is the opposite. So guess what? When we stick these 2 bricks together, the flux through those 2 surfaces are going to cancel each other out. Okay, so now we have, let me back up here. Now we have a longer brick, okay? And, oh, wait, it does look like a brick. How many sides does it have? 1, 2, 3, 4 all around, 5, and 6, okay? So this still is, we can think of it as a sub-brick, except now we can add up the 2 fluxes, and we can also add the corresponding 2 right sides. All right, so here's the approximation for the first brick. Here's the approximation for the second brick. We add them together, okay? But we said that the fluxes through the sides that we stick together are going to cancel out, okay? So in this case, we're attaching along the x-axis. So our normal vectors are I and negative I, okay? As I said, the vector field is the same on both sides because those are the same point in the solid, okay? So these 2 fluxes are going to cancel out. All right. And of course, what we get is the sum of the fluxes through the combined 12 sides. But no, 2 of those sides are gone. So we have 10 sides that combine together, okay? 8 of them combine into 4 sides, and we have the other 2. Okay, so again, we have a sub-brick, and the combined fluxes, let me split out over here, the combined fluxes through the 6 sides of the 2 bricks combine to form the fluxes through the 6 sides of the bigger brick. And on the right side, we have the sum of the 2 divergences. Okay? So notice that only the x-coordinate change, okay, because we are assembling the wall along the x-axis. Y and z are changing. Okay, so I only have 2 hands, so I'm not going to include visual aids to attach a 3rd brick, but we can do it in our imagination. Okay? We have a 3rd brick, and we have this approximation for the 3rd brick, okay? And what happens when you attach the 3rd brick to the end of the 2nd brick, you get a much longer brick, okay? And once again, those 2 sides, the fluxes of the field through those 2 sides are going to cancel out, okay? Because again, one of them has normal vector I, the other has normal vector negative I, okay? So again, you're going to make a brick, a longer brick, but you still have 6 sides to the brick, But now you keep doing it until you get the entire interval from A to B. Okay, so it really does look like Lego, doesn't it? Okay, you have little bricks joined together until you get the entire interval from A to B. Okay, so now we are done with a major part of this wall. Okay, but of course there's more. Okay, so what are we going to do? We are now going to build to the side. Okay, so again, if this were an actual wall, we're going to stop there and build upwards. Okay, but we have a solid brick. Okay, so what we're going to do is we're going to do exactly the same thing that we did for this portion of the brick, of the solid brick, but moving to the right. So now the y coordinate is going to change. Okay, we use exactly the same y coordinates for this because we're only moving along the x-axis. Okay, so now, okay, there's another one, just like we did over here. Okay, so we're now going to attach them. Now I have two hands. We're going to attach them now side by side instead of, what was this, front and back, I guess. Okay, but it's exactly the same idea. Okay, the flux through this side of the brick, the normal vector here is j, okay, because it's along the y-axis, okay? But over here, it's going to be in the opposite direction. It's going to be negative j, okay? So when you stick them together, okay, all the vector fields on this side match exactly the vector fields on this side because they're the same point in space, okay? So when you stick the two bricks together, then those vector fields, those fluxes, are going to cancel out, okay? And do we get a brick? Yeah, okay? That, once again, is a solid brick if you cement those sides together, okay? So the top and bottom, again, form one, the two tops form one top, two bottoms form one bottom, and so on, okay? But you have that left side and this right side still left over, okay? So therefore, we can play the same game as far as adding the contributions is concerned, okay? But this time, we're adding more divergences, okay? So instead of just one row, we're adding a second row, okay? And then we keep going, okay? We keep going, sticking them side by side by side until now you get the lowermost layer, okay? So now we're making cake, okay? That's probably a better, yummier analogy, okay? So when you finish that, you get, as the contribution of the divergences, a double sum, okay? J from 1 to L, I from 1 to L, J from 1 all the way to M, okay? Notice that the Z coordinate is the same, okay? Because it's just the lowermost level, okay? So guess what? Okay, you're smart people. Repeat now for a second layer, a third layer, a fourth layer, and so on and so forth, okay? So what's going to happen then? Same idea. This time we're going to stack the bricks up together, okay? So now, the flux going through this surface, the normal vector is k, but for the flux through this bottom surface, the normal vector is negative k. So when you cement them together, those fluxes are going to cancel out, okay? So yeah, there you go. That's what's happening in your neck of the woods. So we are adding the divergences together. We now have two layers, but we keep going. Keep going until we do the entire brick wall, okay? When we are done, the flux that we get is the flux passing through the 6 sides of the brick, okay? The divergence that we get is the sum of all the divergences through each of the little subbricks, okay, times delta V, okay? So of course, we have a triple sum there, and what happens if you take the limit as n, m, and l all go to infinity? We get a triple integral, okay? So that is not exactly a rigorous proof of the divergence theorem, but it gives you some intuition about it. All right, so we did a triple integral over a tetrahedron. Now, of course, all the triple integrals that we learned about in chapter 3, it's all fair game now, okay? Here's an example where we have a solid, which of course could be expressed either in spherical coordinates or cylindrical coordinates, okay? So if you need a refresher, of course, we have videos to remind us how to create a triple integral using cylindrical coordinates or using spherical coordinates, okay? If you were to find the flux directly, then you're going to have to parametrize the surface of this hemisphere, okay? But you have another region, another surface, the bottom of this snow globe, okay? So to be a solid, you must have surfaces entirely surrounding your region, okay? So to compute the flux integral directly through the boundary of the snow globe, you're going to have to set up two flux integrals, okay? And of course, that's going to be more work than just a single triple integral. Okay, so, oh good. Okay, so no video over 1 hour this time. We're actually under 40 minutes. So, I hope you enjoyed the divergence theorem. In our next video, we're going to finish this chapter and we're going to talk about Stokes' theorem. Kind of different, but again, it looks a little bit like Reed's theorem. Okay, so until then, I hope you enjoy the rest of your day, and I'll see you next time. Bye-bye.